And this is close to when I was finalizing the design. So how it was all done, it's just a Python program. I write a lot of Python, have done for a long time, very comfortable with Python. I know how to do a lot of things in Python. Why would I use anything else when I already know how to do all these things in Python? I can leverage all of those skills. Python, of course, comes with a huge ecosystem of useful tools that you can use. And the particular tool that I found and was very excited about is called Shapely. And I'll talk about it more in a moment. So it's a Python program that I just typed in to generate that whole PCB. It uses Shapely, and it's built on a foundation of Shapely with other layers for doing PCB-specific stuff. And it outputs, just using regular file output, Gerbers, which I then send directly to the PCB house. So there is no CAD involved in this board. So Shapely is a library for computational geometry, which makes you sound smart if you say it. But what it really is just manipulating shapes at scale. So it has a system for representing polygons internally. You can intersect them, you can do a union of them, and other interesting things. This, I think, was new to me. So this is a line. It doesn't always do polygons. Sometimes it does infinitely thin lines. You can inflate that line by a given amount. This is the set of points that are all within a fixed distance, which is half a unit, of that line. So this is actually quite an incredibly useful primitive. And Shapely just does it. You just define the original shape, and you inflate it, and you get this polygon. So this comes up a lot. And the same is true if you specify a negative distance, there's erosion, which takes a polygon and shrinks it. So you've got some fancy stuff in there in a toolkit for creating shapes, and it's already been debugged, works great. So it represents things like these smooth curves with line segments, and you set the epsilon factor of how accurate you want it. So nothing is actually, everything is just a polygon. It's just that you can't see the steps there. All right, so Gerbers. So Gerbers are the file format that we use to send to the PCB house. And Gerbers are specific to photoplotters, which are the traditional method for making PCBs. Here is a photoplotter. The tape gets loaded on with the Gerber on it, and the photoplotter contains an amazing contraption, which is a cathode ray tube, which exposes the various elements on the printed circuit board that make up the printed circuit board onto a piece of film, and then that film is then transferred onto the PCB. Nothing I said was true. It was true once, but of course, things have happened. That was a long time ago. They're rasterized now. It's just a laser printer with a special output. So what you do get is a photoplotter emulator, right? So they take our Gerbers, which are just lists of shapes. They run this ancient code that nobody dares touch, which turns it into a giant raster image, and that's what gets made into the PCB. You can see the pixels if you have enough magnification on the final PCB. So Gerber format has a lot of details, which are historical, right? Because it's legacy system, it has things like exposing an annulus, a ring, in there, and that's part of the Gerber format. And if you look up the Wikipedia page, there's section after section on the various tricks you can do in a Gerber file. Don't need to do any of that, because I'm just talking to an emulator. So you can just give it a vast list of polygons, megabytes and megabytes of polygons. You don't have to use all of the fancy features. You can just use one. So the whole board is just a colossal list of polygons. All right, so that's the how. So Python, Shapely, Gerber output into polygons. I did a few small tests where I just uploaded files, and it all seemed to be working out. So then the big job of laying out my board. And this is for the times in 2020. This is what I was doing a lot of the time. So I've got my code here. I run it, and a couple of seconds later, I've got Gerber V, the Linux preview. It updates. I look at it. I go back to this, change the code because it didn't work. That's my CAD-like development cycle. So it's a lot like if anybody's used OpenSCAD. It's the same sort of experience. You type in some text, you see the result, and you close the loop. So just iterative refinement as you look at it, and it's not quite what you want until you do get what you want. All right, so design principle here is to have a lot of parallel traces. As you can see on here, these flows, these traces all remain parallel, and I want to maintain not only trace width for the minimum design rule for the PCB I'm using, but also trace separation. Trace separation has to be constant and held to an absolute minimum to fit everything on the board. I don't want variations in trace distance, because I'm at the absolute minimum here for my design rules. So these are rivers in some layout systems, right? So here's an example of riverization, if you like. So here's a small QFN with 20 connectors. Take each of these signals, output them, and then join them into, eventually they flow out on the right-hand side, and they've been turned into a river. So every pin is now that isn't power or ground is now connected to the output. So that's all the meaningful signals are now a river on the right-hand side, which flows to the right. So that can then be joined up with other stuff in a completely regularized way. Moving a river around is not as easy as you might think. So this guy has a rake with tines pointing down into the gravel in the garden, drags the rake along. If he drags the rake perpendicular, then the distance between the grooves he's making remains constant. If he pivots the rake around this end, then that also keeps a constant separation between the grooves. If he pivots the rake around this end, he's turning to the right, and he also keeps that same constant separation. Those are the three things he can do. He can drag forward, pivot left, pivot right, and provided that's all he does, he'll guarantee to keep the distance between these constant and not have any violations. If he drags it diagonally, he's messed up, right? And then the rule is broken. So here's an example. Here's a river starting, and we're going to move across. So these are the 9 signals of the river, right? So that's moving forward. Here's a 90-degree turn to the left. So the distance requirement has been satisfied by this. We can go forward a little bit and then do a 45-degree turn to the left, still constant, and at no point do these signals get closer than the absolute minimum. And they always are at exactly the absolute minimum. So it's completely satisfying that constraint. And here is a pivot to the right. So this is kind of an interesting move that I found, that by varying this angle of this transition, you can do a little shimmy. So this is how you move a river a little bit to the left. So it was aligned here, and now it's moved over a small distance to the left. And so this is a simple geometric primitive for getting the river lined up. So it's like driving a really awkward vehicle around the place that can only do certain things to get it, and you get a certain feeling for how you can get things lined up. So this comes up when you try to align 2 rivers. How do you do that? Well, carefully. So here's the finished board. lots of rivers going on. These, you can see there's a huge amount of parallel stuff and nice organized turns. These ripples are it doing those small shimmies to try to get it aligned later on. So you can sort of see the kind of feeling you get. One initial comment that people made, which stung me deeply, was you must get a lot of crosstalk. But because I'd selected my design rules, right, with the rule of thumb that the track width is separated by 2x, there is no real risk of crosstalk because it completely satisfies that design rule that the track width, the separation between tracks is 2x the track width. I think it just looks wrong and dangerous because people don't make boards that have such rigorous parallelism. Everything here is occupying the minimum space required by the design rules for the PCB. So it's super dense, it's maximally dense for those design rules. So here's another way of thinking about rivers using one thing that took me way back is to turtle graphics. So turtle graphics back in the day, from perhaps some of us did it in school. Turtle graphics, you have a turtle who drives around a piece of paper. So to draw this particular thing, you go forward a little distance, 3 millimeters. You go left 45 degrees, turning the turtle, and then you go forward 4. And that's how a lot of the controls worked for the routing. And it's the same for a river, right? We might go forwards, turn left a little bit, which involves, for a river, this quite complicated distance preserving move, and then you go forward. So everything was actually driven by turtle graphics for this one, with special things for joining two rivers and for connecting rivers at each end. And there's the finished board. I showed it earlier in the Gerber view, but this is a render of the board. So all of the river routing worked fine. At one point, I actually did rotate the FPGA because the assignments were, sorry.
So have you ever updated your river manager to maintain length of all the traces when they turn?
Well, you can sort of see it here on the HDMI. Sorry, question was about trace length. Here, this is the HDMI connection, right? And which I did take advice to maintain trace length. So yeah, these are all carefully made to have similar trace length on the right-hand side. So it is possible to do that, but it wasn't critical for what I was doing. So everything worked out with the river routing. At one point, I did rotate the FPGA by 90 degrees, and that was surprisingly easy. That was just, I mean, I'm not saying everything was quick, because it was not quick to do it this way. But that particular thing, which would have been a huge redesign for the Scarab people, for example, was just a couple of hours to rotate the FPGA. So some things were very slow. I'm not going to sugarcoat it. Some things were very much quicker than using traditional CAD tools. So something came up. So obviously, this works great. Taking a huge batch of parallel signals and arbitrarily routing them to this other chip, that worked great. This does not work great. These are two SPI flashes, one for the GPU, one for the FPGA. And their pins aren't really lined up with what you want coming out of the FPGA. They're fixed function pins, no pin swapping possible. So this is the first one I did. And I just had to draw endless pieces of on scraps of paper. I've got them actually stuck on my wall until I found out the particular magic way of getting the signals routing through without any vias. Now, that was time consuming. This is a second one I did, and suddenly I realized you just route the river underneath, and then tap into the river at various points to get the arbitrary hookup you want, just using vias. Of course, they're free and cheap, and so long as you've got space to do the vias, you just put the vias in different places to make the connection. And so I did it once in a sort of one-off way for this. What you really want when assigning pins is a way to permute the signals in a river. I want to take the river, arbitrarily swap the signal order, and then the river is exactly right for where it's headed. So it's just a crossbar. So here we've got 3 signals. By putting the connections between them at different points, we can arbitrarily swap these signals. You just put a different pattern of pegs in the crossboard. And so this is the output of a little macro I made, which does arbitrary signal reassignment. There's a river coming in here. It figures out how to twist it just enough so that the design rules for the vias are still satisfied. It places these vias, and there's the green coming out, which is perpendicular to the yellow, and there it's turned back into a river. So river coming in, river going out, with a completely arbitrary signal order, which is just defined by a Python list, nothing else to think about. And so that used quite a lot in later projects for taking rivers and reassigning the order. And once again, it's like Bob Ross. Once I'd done this thing and I had this Python utility, I just say what signal order I want and it's done, right? There was no more thinking about, no sitting down and having to lay out and find a geometric expression of what I actually wanted to do. The computer did it. So I think at that point, I had embodied the original goal of the project. Okay, so that board came out, and it sort of worked. Everything was fairly successful. What I got interested in next was less ambitious boards, because it was a lot. What if, when you're making a circuit board, you just list the parts that you want, and it just makes you a pretty terrible circuit board with no effort on your part? I would like this, because I don't like hooking things up with breadboards or jumpers, but I often end up doing so. What I would, and boards in those happy times were very cheap and very quick. So I'm willing to wait 5 days for a board to come back in exchange for not having to mess around with quite fragile and brittle prototyping. So one could imagine making a prototype board object, adding the MCU, adding some peripherals, which get added and assigned to pins, and then save it as your board, and then that's it. Nothing else to think about. And in fact, it's true. So I made it. Now, I'm not going to say this board is great. It is somewhat better than a breadboard, and it's a bit better than having a bunch of DuPont connectors flying around and coming out all the time. So there's the MCU. Every signal of the MCU gets turned into a giant river going across the bottom. This is a 100 by 100 millimeter board, which is the maximum size you can order cheaply. And then there's all the peripherals are placed up at the top edge, just in the order that you specified, with obviously just vias connecting them up to connect them to their arbitrary pins. And the tool knows enough about what is a legal pin for everything, like it knows which are the UART pins for the UART, for example, so that it doesn't make a board that can't be used. And then it's done. And then it comes back, and you solder everything together, and you've got a robust prototype with not terrific electrical characteristics, but it is done. So, and here's the actual physical one ready to be assembled. This worked very well, and I did maybe 10 different things this way as I just messed around with stuff. And I didn't have to spend very much time after I got all of my parts added in, right? Obviously, each of these things had to be invented, and I had to lay these out. After that, they were reusable components. One could imagine ordering a set of stuff from your favorite supplier. They could make you a board and provide sample code for actually getting it going. It wouldn't be that hard, and it could be completely automated. So there's a possibility there. However, I didn't pursue that because, obviously, distracted. What started next was a project with a small, compact board that I started a few years ago that I've just finished. At this time, I was wasting a lot of time doing stuff with a game. And why did that game hypnotize me? And it's partly because it's cell-based. So in PCB design, we don't typically have any constraints. You can put anything anywhere. It's a blank slate, and that's kind of helpful sometimes, but also operating within a blank slate where anything can go anywhere, it leads to you painting yourself into a corner. Typically, when you're messing around with Factorio, you're moving around blocks, it's grid-based, everything's constrained, you tend to do copy-paste, reuse components. So something I'd been interested in was doing cell-based layout for PCBs and trying to explore that space and see how well it worked. Cells are a lot easier. You can size the cells for the design rules of the PCB that you're using, and then you just can't go wrong. So long as you can legally place things within cells and you don't break that rule, you're automatically kept within the design rules of the PCB. Another thing that I'd been meaning to try out since 1988 was not using a square layout, but using a hex layout. It seems it's underexplored in layout of using a hex grid because it has 3 directions of connection, and so has some interesting properties. And here is something that I actually used a lot, which is how to do signal routing using Lee's algorithm. So you want to go from here to here. These are the obstacles. You just expand, counting up along a sort of an adjacent wavefront until you reach the destination. And then you just follow the track back 5, 4, 3, 2, 1, 0 back to the origin. And that's your path. And so there's no particular smarts to doing routing. This is easy stuff from the figured out in the 50s, but on a hex grid. So that is the extent of the automation that I needed to implement to get routing going. There's the finished board. So it's a 30 by 30 millimeters. There's the microcontroller. There's the flash, USB output pins, and then on the other side is a display connector. So one thing that people immediately pointed out is that the MCU is skewed by exactly 30 degrees. And the reason for that is to make the connection from the MCU, which is obviously most of the pins in the board, lines up nicely with the hex grid. Hex grids are obviously offset by 30 and 60 degrees. Zooming in a bit, you can see there's something funny about this board, that all of the signals are actually following the ordinal axes of the hex grid. There's a little bit of a transition zone as we leave the world of rectilinear coordinates here as we bend them around, and then we're in hex land and everything is routed on the hex grid. And here's the top layer. It's just a 2-layer board, nothing ambitious. And you can kind of see hex domain happening here. This is weird, right? This is a little squiggle, because there is no axis going straight down. There's axes you have to line it up one way or the other. So it's either going to be horizontal lines are legal, All vertical lines are legal, but not both. So here it's trying to get down through here by doing a series of little trickles down through the hex grid. So I did cheat in a few places where I just jumped the gun and just went for a vertical line, but mostly I just let the hex router figure it all out. So here there's a hex routed pin going down to the clock. So zoom in. This is the SPI flash. These are the signals coming around hex routed, and here you can see the awkwardness that I did not fix. So it's the transition that's hard. So you've got the actual official footprint of the device. There needs to be a transition zone where you go from its coordinate system, which varies by every single part, into this hex grid zone. So everything has to have not only the footprint, but also how you transition into the cell world of the hex grid. So lots of awkwardnesses that I just shrugged and said good enough. So you can see almost every single signal pin has horrible little shimmies and dangles as it tries to get itself into the hex grid. Well, when you're in hex grid, once you're in the hex grid, everything works out fine. Sorry.
Maybe this isn't a useful question, in which case I'm happy to talk to you afterward. It seems like you could just do a single line from the centroid of the pad to whatever the parameter intersection is.
Yes, indeed. You could take a single line from the centroid of the pad onto the nearest hex grid point, and this occurred to me very much later after I'd frozen the design. So, thank you. Okay, and I think that's it. I think this is a good one, and I think it would be possible to assemble a large library of reusable components with their associated routing to get them onto the grid and produce a design system which was somewhat interactive, where you're dragging things around with near instant auto routing on the hex grid, because that's very amenable to highly parallel solutions. It could run in a shader, for example, right? So you could imagine laying something like this out, pouring them onto a sheet, and having the routing show to you immediately and interactively as you move the parts around. It doesn't seem that hard, and it seems, because it's cell-based, it does scale up to very parallel solutions. And that is all I have, I think. Thank you very much.
So, I think the next step is to pitch a manufacturer on hexagonal packages and micrometers.
All of them? Because there's always... No, I think getting much better at managing the transitions is probably the way.
Yeah, I use Python scripts and KiCad to generate RF antennas on the inner layers. It's kind of hard to lay out copper on the inner layers of KiCad.
Right.
But it kind of has problems in the ERC stage. Do you do any kind of electrical rule checking with your scripts, or is it kind of just kind of eyeball?
I did. So it's actually not very hard to do electrical rule checking, right? You just take all the polygons, inflate them, and then look for intersections. So every distinct net got inflated, and then there's a check for intersection. So I did have that, or at least part of ERC checking. It's remarkably easy once you're writing code to make anything you want in the domain of shapes. Right. In a sense, once you're writing arbitrary code, I mean, as I'm sure in the scripting, but I had Shapely, which does all of that as it's just its bread and butter. So it was not hard.
I was looking at, so this is super cool. And it makes me think of a lot of there are like a bunch of problems that I think about that are combination human intellect and like if only I had a machine to do the grunt work for me. And so like things that I think about where I really wish that I had techniques like this, like reverse engineering, right? Like if I had a machine that could do transformations on or and the classic example is like theorem proofers, which they call tactic-based, where you say, make the following transformation on my theorem, and then now I can get it closer to proving this other thing that I want. And the machine tells you, yes, you're allowed to do that. And so I've been thinking a bunch, like as you were, I've been noodling in the back of my mind as you were talking about, like, is this kind of a direction that you're thinking about for more complicated boards of being able to, it seems like you have the full hex grid mode and you had the human guided, full river guided mode.
Right.
And so do you have like ideas for how to mix these things?
Well, I'm probably going to explore hex grid mode in an interactive way. A lot, I mean, yes, I did look at SATs and how they might help. And then I went away from that and went to very crude things, right? Where to put your energy. I mean, it's sometimes, right, there's obviously a lot to explore. I think it's relatively unexplored as far as I can tell. So maybe aiming a bit lower rather than full automation. But absolutely, I mean, if anybody wants to suggest something as a collaboration, I'm very interested in that kind of stuff.
So one thing that struck me about the original is how nice the curved traces looked.
Right.
And that's something you kind of lose with this.
Oh, yeah.
I think part of that is like when you're working with polygons, you can do like unions and expand the boundaries really easily. You can just kind of move the whole thing. Have you thought about having like a different intermediate representation, like a bunch of links maybe that are the case that you can kind of relax in a way? So you do the routing on the hex grid and then you do some sort of separate relaxation to give a nice curve.
Yes, but there's a trap, and the trap is aesthetics. So one thing that I got as a criticism from some people who know about PCBs is, when I showed them the original one, is you have a lot of 90-degree bends. 90-degree bends don't matter. We'll die on that hill. They did once, they don't now. So you're creating designs which are visually pleasing to us in some ways, but they're machine generated. They're defined by their function. So the fact that I have this looks wrong, and it looks like somebody really messed up and ought to be fired, right? Get me a new layout guy. But the key is not to care, to let go of how it looks or how it makes you feel, because, I mean, when we're making ASICs, nobody looks at the routing and says, this is horrible, right? The machine has done it, and it satisfies, it's a correctness-preserving transformation from the intermediate representation that does meet its functional requirements. How it looks to us, we need to... So it's a constant battle of making it look pleasing to me versus, so...
So do you have access to an electromagnetic field solver? I would love to run this through like microwave office to see what the
Yeah,
fields look like on this at radio frequencies.
because it's unusual.
It is unusual.
Right,
I mean,
yeah.
I've had RF engineers sit there with shapes
Right.
because the shapes become components at certain
Right,
frequencies.
right. It probably has exotic properties.
Yeah.
So, okay.
You thought instead of going all the way to Gerber to go to like a PCB file that you can, and then you could use your river routing for where it mattered, and then do some other easy
Right.
stuff instead of having to do it all.
Yeah, it's sort of hybrid approaches. I've never liked that. The first time I saw embedded SQL, for example, right, it's like nuts and gum, right? There's two things that don't exactly go very well together, and you're sort of constantly dealing with this transition. So many people have asked about a plugin for KiCad. It's hard to imagine them working well together, right? Maybe you could have a river routing part of it, but The other thing is that Gerbers, as I use them, were very, very simple, right? Just a flat list of polygons for each layer. And that interfacing with KiCad involves a whole other layer of working with their representation. So
So I'm an RF engineer, so obviously this scares me. And I guess the question I have is, for every signal you have a ground path, and so any thoughts about managing ground paths and thinking that for every trace there's an invisible path that goes through the ground. How do you manage that?
So you're talking about this sort of thing, this one.
Yeah, but especially when you change layers and
Right.
have vias, you need
Right.
to have a place for them to turn.
Sure. So all of these high frequency signals did not. Right. So all of the high frequency signals, which are not that high frequency, they're like 30 megahertz square waves. There's a continuous ground path below all of these. So, like all of us, I'm just winging it and hoping for the best. Well, not all of us, not like you, but it seemed stable. In the 1K run that I did, yield was good and performance was okay. So that's all I know. Okay.
Do you add vias, like ground vias, stitching vias, algorithm? Like, how is ground handled as a net?
I actually can't remember what I did about ground. I think I just put scattered vias where there was a gap. So, okay, maybe last question.
Like other existing tools, it's reminded me a lot of what you've heard of JetX, JetX. They have a code to automatic PCB layout
Oh,
tools.
okay.
And I was just curious if you experimented with some of those.
Haven't. I thought I was the only one doing this ill-advised. Oh, okay. And are they a startup? Are they? Oh, okay.
They don't use Python, they use a stanza language.
Oh.
Their code is to
Oh, okay. I'll take a look. Yeah.
using tools like that as part of this.
Okay. All right. All right. I think that's it. Thank you very much, everybody.